We're going to go ahead and get into what's called covalent bonding. And you've seen a little bit of this already. If you want to, I don't know how much I'll follow this section, but it does talk a little bit about covalent bonding. And so in your book, it talks about these compounds that are called molecular. They're on page 183. So what we just went through was ionic. Ionic. So what do you have to form an ionic compound? Tell me the things you need to have. You gotta have, you gotta have positive and negative charges, right? How do they get positive? They lose electrons. Okay? And the ones that lose electrons are the ones over here, right? Okay? And then how do you get anions, which are the negatively charged particles? What do they have to do? They have to gain electrons. They have to gain electrons until they get what? What's that? Until they full. And so that full, most of the time, is how many? 8. Have to have 8 total. Have to lose to get 8. Have to gain to get 8. It's called the Octet Rule. Okay, so what if they don't want to lose? Let's say we have 2 elements that don't want to lose, but they want an electron. Both of them want an electron. They don't want to lose, but they both want an electron. How do we deal with a situation like that where we have this periodic table outline and we kind of know what areas tend to lose and gain electrons, and so over here in this section, we'll eliminate the noble gases because they neither gain or lose. But we've got a little section over here. It's not very many elements, kind of like in this area right here that we're talking about. This area where they'll tend to want to gain electrons. But we want to see if they can form a bond and get 8, but they're not willing to lose to the other one. Okay, so we're going to pick a couple out here. We're just going to pick a couple out. So we're going to pick out. We're going to pick out bromine and fluorine. Those are the 2 we'll pick out. So we write the electron dot notation for fluorine. Okay, and then we're going to do the same for bromine. They both want an electron. How many do they need to get 8? 1. 1 each. Now, if you would look up the electron affinity for fluorine and bromine, they're like in the -300. So like if you did electron affinity, you kind of know what that is because you studied it. And as you go down the group, the electron affinity became less. And as you went across the period, the electron affinity increased going across. So these both really want electrons. They're going to give off a lot of energy when they gain electrons. So they don't give them up, but what they're willing to do is recognize that they can work together to get the 8. They can compromise a little bit. Okay? They can give a little bit of themselves as long as the other element's giving a little bit of themselves. Okay? So I'm going to rewrite that here. And I'll show you kind of what will take place. So then, here's fluorine. I'm going to write a little fluorine, a little bit different arrangement. I'm still going to have the 3 pairs and then one unshared pair like there. So if you notice, if they're close to one another, so they're close, they're moving around, they're close to one another, fluorine is attracted to this electron that does not have a match. And bromine's attracted to this electron that doesn't have a match. So they decide let's get together. And when we get together, it'll look like this. Now the question is, does everything have 8? So you're like, well, I can't see the difference. Well, what you can do is you can go, I'm going to cover up this one. Does bromine have 8? Mm-hmm. Fluorine. They're satisfied. They have 8. Okay? So the analogy that I used, and I think it's okay, a bond is what holds two elements together. So an ionic one we did, when we did, yeah. So go ahead and put those two together and see how they would go together, and go ahead and place them together, and we'll see if you're right or not. We're getting into some things we're going to do next semester, maybe a little bit this semester. Yeah, well, this semester, next week, I'm putting these together. So it's not a stretch that once we do this, when we start putting in ones together a little bit more complicated, that'll be a little bit easier because you'll at least see it, examples of it. Okay. Well, I think I've given you enough time. So we do our nitrogen. It needs to pick up a total of 3. Chlorine. This chlorine has 1. It'll come down here. Chlorine's satisfied. Nitrogen's not. So we have another chlorine, a second chlorine, that's willing to give 1. It'll come in here. Kind of like puzzle pieces. Nitrogen has 7, needs 1 more. It'll come over here. You keep doing that until everything has its 8. Does everything have its 8? You bet. You bet. And then that's sharing. They're both sharing. So it's like the calculator example I did with Bryce. These 2 electrons that are here are being shared between both. They both have a hold on that, their electron and the electron that they're picking up from the other element. So they're sharing that spot. Any questions? Okay. So that compound would be NCl3. So it's kind of like we did with ionic, but we're doing it with covalent, and we're just figuring out how many we need of each to fit our puzzle together. So these are puzzle pieces that we need to fit together. And these puzzle pieces, where you have lone electrons, they fit together. They're like a puzzle piece that comes together and interlocks and holds together. Got one last one to do, and this is the toughest one, but last class there was quite a few students that got it right, so you guys are be able to have success on this too. So we're going to do oxygen. Right there's oxygen, and then we're going to do a second element, and we're going to do carbon. Now, carbon is going to look different from what you're used to drawing and what you think should be drawn. Because usually carbon is drawn this way, and because we kind of follow that sequence. But carbon is unique in that it kind of separates all its 4 electrons into 4 different orbitals where we can have sharing take place. I want you to figure out the way that those two can go together. See how they can go together. So it might take you a little bit extra time to see how they fit together. But maybe not. Maybe you guys have a good grasp of how these are going to fit together. So go ahead and then write the formula for it. I kind of like these. If you can see the puzzle pieces and see how they need to go together, these are so easy to figure out ratios. And the charges are really easy to figure out ratios. And so this is a big part of chemistry, this understanding of how things can go together and what their ratios are and why they go together the way they do. Okay, if you would take organic chemistry, this is the basic part of organic chemistry. I told the other classes, ionic compounds, there's probably over 1,000 ionic compounds, okay, that you could put together with the combination of elements in the thousands. Okay? When we're talking about or carbon base or anything that's covalent, we're talking about billions. Not thousands, but we're talking about billions of different combinations we can put together. So you got this pharmaceutical industry that are making drugs, creating enzymes, creating blockers, like for cancer. And they're putting together these proteins, and these proteins are so complicated at how they go together, and they're all carbon-based. And they're just different structures with a whole bunch of carbons hooked together with other elements that make the proteins. Like, for example, you guys did some things with amino acids. I'll show you one amino acid that you did. I think it's not methyl, but it's, I know there's 20. And I know that there's a base to it. Maybe you guys can tell me what it is when I write it out. Might be methine, I think. I don't know. I know there's alanine and aniline, and you can go on and that. I think you've done some of that before. So kind of getting back to this one, let's see if you put your puzzle piece together right. So here's your puzzle piece. There's carbon. I'm going to rewrite it over here. I'm going to bring this oxygen. I know it can only link where we have openings. So I'm going to bring this one oxygen down here. I'm going to put it here. And I'm going to share both of these. We'll come in and share both of those two spots. And so we'll have an oxygen here. And then these two are not part of the bonding. The two pairs. So does oxygen have 8? The carbon doesn't. Carbon has 6. So we bring another oxygen in down here. We take those lone electrons. We pair them up because they can share. And then we show our 2 unpaired electrons. And so what's the formula there? Gee, CO2. Have you guys talked about CO2 much in biology? Yep. Carbon dioxide cycle. We make CO2. Plants take it in to make proteins and those type of things. So there's CO2, and that's how it's hooked together. This is called a double bond. So when we get into this, if we have 2 places that are being shared between two different atoms, that's called a double bond. Where the one we had before it, these are single bonds because they're only sharing in one pair is only being shared between the 2. So those are single bonds, single covalent bonds, and these are double bonds because it's a sharing. So do you think that would be a stronger bond than this one? Yeah. Yeah, it's going to be stronger because there's 2 of them that are being shared. So that's a tighter bond. That's harder to break. So if we wanted to break that apart, that's what happens in photosynthesis, is that breaks apart, okay, with water. And then it reforms into glucose plus oxygen gas. So we could actually show that if we wanted to. So that's CO2, and that's how it goes together. And then all these compounds we're going to put together covalently are going to do that. So one last thought leading in tomorrow that we'll talk about tomorrow is I want you to get out your periodic table and I want you to look up the electronegativities on your periodic table. You do have it on the back of your periodic table right here. You want to look on the back and you want to look at electronegativity. It's called Pauling's. And it's the upper right-hand number on the back side. And these correspond to what's called electronegativity. And we're going to give you a definition of electronegativity here in a second, but we've already given that to you. What is chlorine's electronegativity? 3.16. Okay, what's nitrogen's? 3.04. There's not a whole lot difference between those two numbers. So see these two electrons here? Right here? Both of them have pretty much an equal share of that electron. If the numbers here on electronegativity, now electronegativity, the definition was the attraction for electrons between two bonded atoms. Nitrogen has an attraction of 3. Chlorine has a little bit more than 3. They have pretty much an equal attraction for that electron. Any questions? All right, let's look at carbon. So here's carbon. Oxygen is 3.44. Right? Is that what it is? And carbon is 2.55. Right? Which of those... Okay, so these two that are being shared, which one has a greater share of those electrons? Oxygen. Oxygen has a greater share for those electrons. Okay? So, to give an understanding of what I mean greater share,